Up to this point, we've talked about motion. We've seen many different kinds of motion, but we haven't talked about what causes motion. And what causes motion is forces. And we're going to look at forces right now. I have a hacksaw blade on a board here, and if I pull this hacksaw blade to the side, it pulls back. It pulls back with a certain force. And a force is essentially a push or a pull. I've got a nice table in the book that shows you all the properties of forces and things that you need to know about forces. But for now, we're going to use the force created by this hacksaw blade. And if I pull it a certain distance to the side, it always pulls with the same force. Well, I've got this hacksaw blade connected to a string which is connected to this truck. And right now the truck is blocked so it can't move, but once it starts to roll, it rolls with very little friction. It'll roll very, very freely. I'm going to do this. I'm going to pull the blade to the side so that it's providing a certain force. And I'm going to move these bolts so that the truck is free to roll. And then I'm going to move this board so that the hacksaw blade stays at this exact point. And if I do that, it's always providing the same amount of force. And so the same amount of force is always being provided to the truck. And what happens to an object if I provide a constant force to it? Let's do it. Find out. If we look at the motion of the truck, we make a motion diagram as we've done before. And what you see is the velocity vectors are getting longer, and they continue to get longer. And in fact, if we analyze them, if we take a difference between successive velocity vectors, what we see is we have an acceleration. And if we were careful about this, we could see that in fact we have a constant acceleration. So a constant force produces a constant acceleration. Now we're going to do another test. And you know the answer to this question, even though we haven't talked about it yet. How about if I was to take this truck and pull on it with a force that's bigger than the original force? So the first time I did this, I pulled with the force that pulled the blade this far to the side. Now, if I pull with the force that pulls the blade this far to the side, that's a significantly greater force. So if I pull with a greater force, how will that affect the subsequent motion? And I want you to compare this case, the first case, to the second case. And in the second case, we have a larger force. Larger force, how will the acceleration vary? We'll give you some choices. And let's just do the experiment and see what happens. And if I let the truck go with a larger force on it, here's what happens. The velocity vectors get longer, but the difference in each successive time interval is significantly larger than it was before. What that tells us is this: the acceleration is bigger. Bigger force means a bigger acceleration. And that's exactly what you would have suspected. We have one more thing we want to vary, and that's the mass. So if I take this truck and put a significant quantity of weight in it, this is going to approximately quadruple the mass of the truck if I put these bolts in it. So I'm going to quadruple the mass of the truck. We're going to pull with the same force as we did initially. How is the motion going to be different than it was in the first case? We'll give you some choices. And again, let's test it and see what happens. 4 times as much mass and the same force as the first case. And then what happens is this: the truck accelerates, the velocity vectors continue getting longer. The amount that they get longer in each time interval is the same, but it's a lot less than it was previously. So what that tells us is this: we still have constant acceleration, but the magnitude of the acceleration is less than it was before. Let's put the pieces together of these experiments that we did. It turns out that if I apply a constant force, I get a constant acceleration. If I increase the force, I get a larger acceleration. If I increase the mass, I get a smaller acceleration. If we put all these together, we get what's known as Newton's second law. And we haven't worked this out so carefully, but in fact, you could do very careful quantitative tests. It would appear exactly this way as we present it in the book. The acceleration is just equal to the force divided by the mass. Now notice, this is a vector equation, and the acceleration is in the direction of the force. As we learn about different forces, you'll see that forces are always interaction between two objects. In this case, I've got the hacksaw blade and I've got the truck. There's an interaction between two objects. So forces are interaction between multiple objects. And so we need to talk about the relationship between forces between different objects. And I'm going to look at another experiment here. I've got these two little spring toys, and the way the spring toys work is this. I push down on them, set this on the table, and then at some point the spring will pop, the toy pushes against the table, and the toy pops up in the air. But here's what we're going to do. I'm going to take this toy and I'm going to push it in, okay? So it's going to push, but I'm going to have it push not down. I'm going to have it push sideways. And I'm going to call this one toy 1. I'm going to call this one toy 2. So toy number 1, the spring is going out. Toy number 2 is just sitting there. But I'm going to put them together so that when toy 1 sends the spring out, it's going to contact toy number 2. So toy number 1 is sending its spring out. As it sends its spring out, it's going to contact toy number 2. I'm going to push them together like so. This one is going to send its spring out. There's going to be an interaction between the two. And here's the question. When I let these fly apart, what can you say about the distance they'll travel? Which will go farther, toy 1 or toy 2? We'll give you some choices. Rather than tell you what should happen, we're going to actually do the experiment. I'm going to take this toy, I'm going to compress it, I'm going to put toy number 1 up against toy number 2. We're going to let them fly apart, and we're going to see which one goes farther. And in fact, what you see is this. They go the same distance apart. They go the same distance apart. What that tells me is, even though this was the toy that was using its spring, this toy pushed on that toy, that's obvious. But this one pushed back on this one. They went apart the same distance. And so even though this was the one using its spring, this one was exerting a force on this one as well. They're exerting forces on each other. And the forces were equal in magnitude because the two toys went the same distance, but they were opposite in direction. The two toys went in opposite directions. They went the same distance. And so the forces between them are equal and opposite. And it wouldn't matter if I compressed the spring on toy number 2 and let them push apart. They go the same distance. The forces are always equal and opposite. This is a very, very deep principle of physics called Newton's third law, and it's by no means obvious. So no matter what happens, no matter which one of these toys is doing the work, the forces between them are always equal and opposite. They always go the same distance in opposite directions. That's Newton's third law. It's a very, very deep principle of physics. But we've seen several different kinds of forces at work here. We had a spring force when I bend this hacksaw blade to the side, or a spring force when I do this. We also have clearly friction at work. We've got weight at work. We've seen lots of different types of forces. Before we can do problems with forces, we need to talk about the nature of these different forces, and we'll do that in the next segment.